new problem. This time we have a ladder that's leaning on a wall. So we have a wall, a vertical wall like that, and there's a ladder that's leaning on the wall at an angle of theta. We're not given theta, it's more of an abstract angle value. So this is theta, and then we also have a distance L for the ladder itself. Obviously, half of the ladder will be L/2. And then also there is a weight mg because the ladder has a mass of m. Okay, that's the mass of the ladder. It's m. There are two reactions. There's a reaction right here, and there's another reaction right there. So two reactions of the ladder itself. Remember, if the ladder is not moving, mu s is the coefficient of static friction, since the ladder is not moving. And also another piece of information we're given is the fact that the ladder the ladder is held on by this surface right here. So there's a friction right there that's holding on the ladder on the surface. So the purpose of this problem is that we want to find the minimum angle theta. So minimum theta at which the ladder will not slip. So we have to think about the forces and the reactions in the x and the y direction. So there's an initial reaction right here. Let's call that R1, and we also have another reaction here. Let's call that R2. That's the second reaction. And also, we can resolve theta into its components. The main component we're interested in is mg cosine theta. So we're resolving the weight of the ladder. So the mg cosine theta is a component pointing downwards, assuming this angle here is theta. And then also there's a frictional force that way. We're going to call it FR. And just remember that FR by itself is mu static friction times the normal reaction. These are the pieces of information we're given. This angle obviously is theta because of alternate corresponding angles, meaning if this angle is theta, this one also has to be theta. And then also there's a component that's pointing upwards as a result of the second reaction. That component is pointing that way, and it's equivalent to R2 sine of theta. Okay, that's a super helpful component in solving this problem. So, the first thing we're going to see is that the system is in equilibrium. As a result, the sum of forces in the x is 0. The sum of forces in the y is also 0. The sum of forces or or the sum of torques around any point is also going to be 0. So we're looking at the free body diagram, and we want to start with the x direction. So we're saying the sum of forces in the x is 0. In the x direction, you can see that we have N2, or rather R2, this one right here. It's pointing to the left, so R2 is pointing to the left. So if that's the case, if this is our positive x direction, so if this is our axis like that, this is x and this is y, this is positive y, this is positive x, it means the frictional force R2 is going to be negative, and then the frictional force is pointing in the positive direction. That means the result is 0. So then we have Fr minus R2 equals to 0. We're going to flip onto the next page and see that our frictional force is equivalent to the reaction at the top. And for convenience, let's call the position of the initial reaction A and the position of the second reaction B. So we know that the frictional force is the coefficient of static friction times the initial reaction. So we see that mu s R1 has to be equivalent to R2. So R2 becomes mu s R1. This is a critical relationship in solving the problem. The next thing we're going to do is focus on the y direction, where we're saying the sum of forces in the y is 0. If you go back, you see that the weight is pointing downwards in the y direction, and this reaction, the first reaction, is pointing upwards in the y direction. So they're on opposite sides, and as a result, we'll see that R1, because it's pointing upwards, and you can recall that positive x is to the right, positive y is upwards. So R1, which is pointing upwards, will be positive, minus mg is pointing upwards. This is 0, so R1 equals to mg. They're pointing in opposite directions. This is another critical relationship. And then the last type of relationship has to do with the torque around A. We know the sum of the torques around A is 0. If you look at the diagram, R2 sine theta is pointing in the counterclockwise direction, so it's going to be positive. And then the weight, mg, the weight is pointing in the clockwise direction, so it's going to give a negative torque around A. So we end up having R2 sine of theta times the perpendicular distance, which is this distance right here, that distance. We're calling that distance L, and we're calling half of it L over 2. Okay, so half of it has to do with where the weight is passing through, so times L minus mg cosine of theta times L over 2 equals to 0. So R2 sine theta, if we solve that, we get mg cosine theta times L, all over 2L. This L will come down, so 2L, these two L's cancel out, so we can solve for R2 sine theta over cosine theta becomes equivalent to mg over 2. In the next page, we continue the problem by saying R2, remember tangent of theta is equivalent to sine theta over cosine theta. And so R2 sine theta over cosine of theta equals to mg over 2. So R2 tangent of theta equals to mg all over 2. And that helps us solve for tangent of theta. We're dividing both sides by R2. So tangent of theta is mg over 2 R2. But if you go back to the second page, you see the relationship between R1 and mg. And so R1 is equivalent to mg. So tan theta becomes R1 over 2 R2. Okay, but then again, going back to the second page, you see R2 is equivalent to mu s R1. So then we have R1 over 2 mu s R1. This is the coefficient of static friction. These two are going to cancel out. So we end up having tangent of theta being equivalent to the reciprocal of twice the static friction. And so we can solve theta using the inverse theorem. So theta becomes equal to tan inverse of 1 over 2 mu s. So hope you enjoyed the problem. We relied on the sum of forces in the x, the sum of forces in the y, and the sum of torques specifically around A. You could have taken the torques around B, that's fine, but we focused on point A. And so the sum of forces in the x was equivalent to 0, assuming that R2 is pointing towards the left and the friction is pointing towards the right. We make those two equivalent. Also remember the coefficient, the friction is equivalent to the coefficient of static friction times the normal reaction, which is R1 in this case. And so we build our first relationship that connects R2 to the frictional force based on the sum of forces in the x. And then when it comes to the sum of forces in the y, our focus shifts to R1 and the weight, which is mg. So those two become equivalent. That way we're able to solve R1 in terms of mg. And then finally, we take the torque around A, assuming that the sum will be 0, plugging in the forces involved. The two forces, the first one is the one connected to R2 sine of theta, and then the second one is the one connected to the weight, which is mg. And so the weight is a distance L2 from the point A, and R2 sine theta is a distance L from the point A. We use those two values and those two forces and their perpendicular distances. We make them equal and simplify to solve for tangent of theta. But then we're solving for tangent of theta after canceling out. And so tan theta is R1 over 2 R2. And we write R2 in terms of frictional force. And we pick that up based on what happened as the sum of forces in the x was equivalent to 0. And so tangent of theta is 1 over 2 mu s, and then we can solve for theta. Hope you enjoyed the problem. Feel free to send any questions or comments, and have a wonderful day. Okay, thanks. Bye.